In this video, we're going to be looking at topic 12A, entropy, and this is part of the IA2 chemistry course from Edexcel. So we're going to be looking at spontaneous reactions and how these are controlled by enthalpy changes and entropy changes, understanding what is meant by entropy and how it changes with temperature, being able to explain different changes of state or chemical reactions by using entropy, being able to calculate not only the total entropy but also entropy of the system and of the surroundings, and then linking entropy to feasibility of reactions and understanding when a reaction is going to be feasible and looking at the differences between thermodynamic stability and kinetic stability. Now, ever since Key Stage 3, you've learned about chemical reactions, and all the way through Key Stage 3, GCSE and the AS course, you've learned that some chemical reactions will happen and some will not, but you've never really went into the detail about why. Now, the first thing that we need to understand is actually every single chemical reaction has an equilibrium associated with it. Now, we've only ever discussed equilibrium when we have equal amounts or constant amounts of the products and the reactants. But actually, every single reaction has an equilibrium. What happens is that sometimes the reaction has an equilibrium that sits so far to the product side that it appears to go to completion. Whereas some reactions have a position of equilibrium that is so far to the reactant side, it looks like they don't actually happen. Now, we know that some will have a position where we get a significant amount of both reactants and products. These are the ones that we've met before in topic 9. But we need to understand that all chemical reactions are a form of equilibrium. So a question isn't actually, will a reaction happen? The best question that we can actually ask is, what will be the position of equilibrium for a reaction? And that's what this entire topic is going to look at. It's going to look at what affects that position of equilibrium, how we can determine it, and it will then lead us into topics 13 and 14 as well. Now, what we know for exo and endothermic reactions is these are all to do with the differences in energy between our reactants and products. So in an exothermic reaction, the products have less energy than the reactants, and this means that they are more energetically stable. So they have a lower energy, and we see that in our reaction profile, where we get something like that. So we have our reactants and our products being more energetically stable. Now, we've said that this, up to this point, this is the reason why the reaction goes. Now, this isn't actually the only reason that exothermic reactions can happen at room temperature, because we can have some endothermic reactions that are going to happen, and we've seen these, but they don't have energetically stable products. So it can't just be about the energetic stability. It must involve another factor. And this factor is known as entropy, and it is governed by the second law of thermodynamics. So before we get into discussing what this actually means, what we're going to find is there's a lot of small bits and pieces in this topic that we'll then pull together towards the end. So the first thing that we want to look at is, what do we mean by a spontaneous process? Now, a spontaneous process is one that will take place without continuous intervention by us. So, for example, ice freezing or the mixing of gases. These are spontaneous reactions because they do not require continuous intervention. They don't require us to be constantly mixing the gases for them to mix. We can just leave the gases and they will mix on their own. We can reverse the spontaneous process by intervention, but this will never happen on its own. So if we have a spontaneous process where we make a mixture of gases, these will never spontaneously separate unless we do something to separate them. So these processes are examined by thermodynamics, which is the study of energy changes accompanying the physical and chemical changes. So we're looking at what's happening energetically, and it introduces this concept of entropy. So from the perspective of thermodynamics, every single chemical reaction is reversible. So again, now we want to change our question. It's not will a reaction go? It's not what is the position of equilibrium. It's now when a reaction reaches a point of equilibrium, what determines if the equilibrium will favour the reactants or the products? So what will determine to drive the reaction forward or not, and to what extent? So we're assuming that every single reaction is going to reach a point of equilibrium, and we need to figure out or understand what causes a reaction to drive forward or go back. And this concept of entropy is then used to answer this question. So entropy is a quantity that's associated with randomness or disorder, and it's a property of matter. So really what it means is it's talking about the distribution of molecules, but also the distribution of energy of a system throughout these molecules. Now, this can be quite a difficult concept to understand because a lot of it you have to think about theoretically or in your head, but we can use specific examples to help us understand. So let's use the diffusion of gases. So we're going to look at the arrangement of particles first of all. So we're going to split it into two. The first part of entropy is linked to how we arrange the particles. So if we have this system of two gas jars, we have gas jars on the right, gas jars on the left. And in that gas jar system, we have 5 molecules. So they have two possible arrangements. The molecules can either be on the right-hand side or they can be on the left-hand side. So each possible arrangement is then given a value. So we're going to call this value W, and for particle 1, we're going to call it W1. And this value is 2, meaning for particle 1, it's got 2 possible places it can be. We can then do the same for particle 2, particle 3, 4, and 5. So therefore, we can work out the total arrangements would be 2 times 2 times 2 and so on, or 2 to the power 5, telling us that we have 32 possible arrangements for these particles. Now we're only talking about 5 particles here with 32 possible arrangements, and only one of these arrangements is going to be this first one where all of the particles are in the same side of the jar. Okay, if we then increase the number of particles, let's say up to 100, this W value becomes 2 to the power of 100. And that would mean that if we were to have these particles and we were to measure or pinpoint each time that all 100 particles were in, let's say, the left-hand side of the jar, this would take 3.2 times 10 to the 22 years. So we can have a huge number of arrangements with these particles moving in this random order, and we would only see them all converging, all 100, in the left-hand gas jar once every 3.2 times 10 to the 22 years. A huge number. Now, we can then apply this to then talk about moles. If you remember, we're not looking at 100 particles in a mole. We're looking at 6.02 times 10 to the 23 particles. So as this number of molecules increases, the number of arrangements is going to rapidly increase. And we need to understand this, that we can have so many different arrangements for these particles. And then we then link it to energy, which we'll talk about in just a minute. Now, to simplify the numbers, we can use this equation where S is entropy, we have K and the natural log of W, where W is your number of arrangements. Now, you're not going to be asked to use this equation or to remember it, but it would help us see the number of different ways or the spreading out of the molecules, how it's related to an increase in entropy. Now, this K is known as the Boltzmann constant, which is 1.38 times 10 to the 23. And actually, in a very nice link, if you take K and you multiply it by Avogadro's number, which is your number of moles, you're going to get a value of 8.31, which you should know is R, or the gas constant that you've met in PV equals nRT. So all of these constants do actually have a link in together. So if you multiply the Boltzmann constant by Avogadro, you get 8.31. Now, you're not going to be asked that in an exam. That's just an interesting thing to understand. Now, because entropy is linked to the disorder of particles and the randomness of the movement of particles, what we would expect is in solids, where the particles are in fixed positions, they would have a low entropy. And we measure entropy in joules per Kelvin per mole. So it's linking an energy value to the number of moles as well as a temperature. So if we were to have a gas, what we know is that gases are not fixed positions. They are going to move randomly. And the more that these move randomly, the higher the entropy is going to be, because the more they move, the more arrangements we can have. Now, this is shown with the entropy values for water. So water vapor has an entropy of 189, which is high, as opposed to ice, which has an entropy of 48, which is low because the particles are going to move less, therefore they're going to have less possible arrangements. Now, when we're looking at distribution of energy, so the second part of entropy, this is similar to the distribution of particles. Now, the energy exists in small packets called quanta, and their distribution between the particles is completely random. The more quanta there are, the more ways there are of arranging them, and the more particles, the more ways there are of sharing the quanta. So it all links in together. The more particles and the more energy we have, the more we can distribute these. So if we have, for example, a higher temperature, we're going to have more possible energy, therefore more ways to distribute the energy, therefore a higher entropy. So whenever we're looking at the distribution, we need to take into account how much energy or how many particles we have to distribute. And that's going to have an effect on the entropy. So for example, if we have these three different setups where we've got table B is 2 molecules, 4 quanta, so 4 small energy packets, and therefore 5 arrangements. Table C gives us 2 molecules, 5 quanta, and 6 possible arrangements. Table D gives us 3 molecules, 3 quanta, and 10 possible arrangements. So we can see that as we increase the number of quanta and increase the number of particles, we're going to get a further wider distribution, therefore higher entropy. So the second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. So we can simplify this by saying that for a spontaneous process, one that does not require intervention from us, is going to have a total entropy change that will always increase, therefore a positive value. So we're going to be looking for a positive S value in order for us to have a spontaneous process. Now what we need to do is we have to look at what is meant by the total entropy change. So the total entropy change of any process is made up of 2 parts. It is made up of the entropy change of the system and the entropy change of the surroundings, or delta S system, delta S surroundings. The species that's taking part in the reaction is the system, and the surroundings is everything else that is around it. So your reaction vessel, the laboratory, all of that is your surroundings, and the species that is actually reacting is the system. And the total entropy is calculated as this equation at the bottom. So delta S total is equal to delta S system plus delta S surroundings. And this is the most important part. For a reaction to be spontaneous, your delta S total value must be positive. So if you have a positive value, your reaction is spontaneous. And you will do some calculations and do examples of these in past paper questions, and we should see some of these at the end of the video. Now, if we look at the entropy of the system is calculated using the formula, the sum of the entropy of the products minus the sum of the entropy of the reactants. And the standard entropy values will be given to you in a calculation in the exam. So you're not expected to know these or to calculate them. You will be given a table of values and then asked to calculate an entropy of system or a total entropy. So you can see that we've got some examples here where we've got entropy of gas, where you can see particularly high values because these are all randomly moving and lots of different possible arrangements. Liquids, a little bit lower, and then you've got your solids, which have got low entropy because the particles don't move, they're in a fixed position, therefore they have much less possible arrangements, therefore a lower entropy. So we can look at some examples of how we calculate the entropy of a system. So if we start off by looking at the decomposition of calcium carbonate into calcium oxide and carbon dioxide, and we'll use the values that were given in the table. So we've said that our entropy of system is equal to the sum of the entropy of the products, take away the sum of the entropy of the reactants. So for our products, we're going to be using the calcium oxide and the carbon dioxide. So we're going to have 39.7 plus 213.6, and then we're going to subtract our calcium carbonate, which is 92.9, and we get an answer of plus 160.4, and then our units is joules per Kelvin per mole. It's very important that you have a sign and units in every single calculation that you do for entropy. Always include a sign, regardless of whether it's positive. Don't just miss it out. Always put the actual positive. Then we can look at another example where we've got the formation of ammonia. So we have the nitrogen plus 3 molecules of hydrogen, giving us 2 molecules of ammonia. Now in this one, we have to take into account the fact that we have these coefficients. So we have our entropy of our system is the sum of the products, again, minus the sum of the reactants. So we're going to have the sum of 2 times our ammonia, which is 192.3, and then subtract that from our reactants. So we have our nitrogen is 191.6, plus our reactants are also the hydrogen, so 3 times 130.6, and that gives us an overall answer at this time of minus 198.8 joules per Kelvin per mole. Again, got my sign and I have my units. And you can see then that we have our 2 answers that we've managed to calculate there. Now, looking at the entropy of surroundings, we can calculate this as well using a formula of minus delta H over T, where T is the temperature in Kelvin and delta H, of course, is our enthalpy value. So you would be given this as well in the exam. So for exothermic reactions, our delta H is negative, of course. So the delta S surroundings is always positive for exothermic reactions. So the entropy of the surroundings is going to increase. For endothermic reactions, where our delta H is positive, our entropy of surroundings is always negative because our entropy of surroundings is decreasing. Okay, so we can use this formula in order to calculate the entropy of surroundings. And again, we can look at an example. So calculate this entropy of surroundings at 298 Kelvin when 1 mole of hydrogen gas is burned in oxygen. So I use my equation. The surroundings is minus delta H over T, giving us minus 286 over 298, and of course the overall thing is minus, so my two minuses are going to cancel each other out, and I get plus 0.960 kilojoules per Kelvin per mole. But for an entropy, I want to have it in joules, so I then multiply that by 1,000, and I get an answer of positive 960 joules per Kelvin per mole. Always check your units. You can do the calculation when it is in kilojoules per mole, as long as you then multiply it by the 1,000 in order to put it into joules per Kelvin per mole. Both your entropy of system and your entropy of surroundings have to be in joules per Kelvin per mole. And there you can see the same answer that we just got. Now, once we've calculated our entropy of system and our entropy of surroundings, we can then calculate our total entropy. So we've just said, for if we take that same reaction, so the H2 plus a half O2, giving us H2O, and we said that the delta H was minus 286 kilojoules per mole. We've just worked out that the entropy of surroundings is plus 960 joules per Kelvin per mole. And we could work out the entropy of the system using those values that we used previously in the table, and we get minus 163.2 joules per Kelvin per mole. And our total entropy is equal to the entropy of the system plus the entropy of the surroundings. So then I substitute my numbers in, and I get minus 163.2 plus 960, and my total entropy is therefore plus 796.8 joules per Kelvin per mole. Now, this is a typical exam question where they will break it down potentially into a structured calculation and ask you to calculate the entropy of system, the entropy of surroundings, and then calculate the total entropy. And you would then be asked to comment on that total entropy, which we'll touch on a little bit later. So there you can see that we've got the same answer. So our total entropy is going to be positive if, and therefore give us a spontaneous reaction, if our system and our surroundings are both positive values. If our surroundings is positive and our system is negative, we have to have a higher surroundings value than the system. If our surroundings is negative and the system is positive, our system has to be the higher number, and that will give us a positive entropy, meaning that we have these spontaneous reactions, and we'll link this into feasibility as well. Now, some key terms that we need to understand. We've covered some of these before. So we've got thermodynamic stability and kinetic stability. And we need to understand that there is a difference between these two different types of stabilities. And you've met them both before. You just need to now understand what the difference is. So thermodynamic stability depends on whether or not a reaction is spontaneous. So this is to do with entropy. So if the reaction is feasible, our total entropy is positive. Okay, so we're looking for that total entropy value to be a positive value. For kinetic stability, this is linked into rates and activation energy. So this is our kinetics. And reactions that have a high activation energy are not going to take place at room temperature. Now, this means that we can have a reaction that is thermodynamically unstable, but kinetically stable. So, for example, methane will not form carbon dioxide and water unless it is ignited. So we can have this feasible reaction, meaning that the reaction will go ahead and could be spontaneous. However, it is a kinetically stable reaction because it's a high activation energy. So we do need to put in a bit of heat or ignite it in order to overcome the kinetic stability. But once we do that, it is a thermodynamically feasible reaction. So we need to understand that we can have reactions that we would class as spontaneous, but because they have such a high activation energy, they are not going to take place at room temperature. But if we overcome that activation energy, then they will take place. So it's very key that we understand the difference between those. Now, if we understand the entropy changes that can be taking place, we can actually predict whether a reaction is going to be thermodynamically spontaneous or not just by looking at the conditions of the reaction and also what we're making and what we're making it from. So, for example, if we look at a change of state, we know that because entropy is linked into disorder or a randomness of the particles and the energy being distributed, we can see an increase in entropy as we go from a solid to a liquid to a gas. I.e., if we make a gas, we are getting an increase in our entropy. So we can then determine and confirm the feasibility by looking at the change in state. So if I look at the first reaction where I've got solid ammonium carbonate being added to pure ethanoic acid, we can see that I'm making bubbles of gas. So I'm going from a liquid and a solid to a solution, some water, and our carbon dioxide gas. Now, this is actually an endothermic reaction, and we would be told this because we see a temperature drop. So that means our entropy of surroundings is going to be negative. Now, despite this, we're going to have a very large change in entropy of the system because we are going from having a solid being put and a liquid producing a gas. That's going to give us a huge increase in our entropy, meaning our entropy of system is a positive value, and we're going to have a higher magnitude of our entropy of system in comparison to our entropy of surroundings, meaning that the entropy total is going to be a positive value, therefore that is a spontaneous reaction. So we're looking this time at the magnitude of these values. So although we've got one negative and one positive, the magnitude of the entropy of the system is so much larger than the entropy of surroundings that overall we get a positive total entropy. If I look at the second reaction where I have my magnesium burning and oxygen in order to form magnesium oxide, we know that this is highly exothermic. It is a combustion reaction, of course. So our entropy of surroundings is going to be positive. Now, because we're getting a solid and a gas forming only a solid, I'm going to see a negative entropy of system because I'm going to have a decrease in my entropy. However, the magnitude of the value of the entropy of surroundings, the positive value, is so much higher than the magnitude of the entropy of system that once again, my total entropy is a positive value, meaning that this is a thermodynamically spontaneous reaction. So not only am I looking at what I'm forming and from what I'm making it, I'm also looking at the magnitudes of my values, and overall, for both of these, we see a spontaneous reaction. If we move on to dissolving ionic solids and water, when we get this dissolving happening, we get two different changes taking place. And this will be discussed further in topic 12b. But we have our lattice structure being broken down, because of course we're going from this solid lattice into a solution where the ions are free to move. And the ions are also hydrated, meaning they're surrounded by water particles. And again, this will be discussed further in topic 12b. We're just touching on it just now. Now, the breaking of the lattice is an endothermic reaction, and it also results in more moles of our particles. So we're breaking up this lattice, meaning the particles can move more possible arrangements. Therefore, we're seeing an increase in the entropy. Now, the hydration of ions, or the surrounding of the ions with water, is exothermic, but as we surround the ions with water, they become more arranged around the particles, therefore meaning they have less possible arrangements and our entropy decreases. So solubility involves both enthalpy and entropy changes, and it is going to all be determined on the entropy change of the system, the enthalpy change of solution, so how much energy does it take to break up this lattice, and of course the temperature of water, because it does always link into the temperature. So we're using our total entropy equation, but we're swapping out our surroundings for our enthalpy of solution over our temperature. So we're just expanding on that, linking the fact that solubility depends on these three factors. So we can then look at an example. So if we have ammonium nitrate dissolving in water at a temperature of 298 Kelvin, we would be given our enthalpy of solution as plus 25.8 kilojoules per mole. I could work out my entropy of the system, remember, by doing the products minus the entropy of the reactants, giving me a value of positive 108.7. I can determine my entropy of surroundings using my enthalpy value, and I get a value of minus 86.6. I substitute that into my equation to work out my total entropy, and I get a value of positive 22.1 joules per Kelvin per mole. So since my total entropy change is positive, this means that this is a thermodynamically spontaneous reaction at 298 Kelvin. And because this has got a very low activation energy, it means that the ammonium chloride is soluble in water. So we're taking into account the enthalpy of solution as well as our entropy. And as long as we get a total entropy value that is positive, we're going to have a thermodynamically spontaneous reaction. So we can then start to look at the solubility in water of some other ionic solids. And you can see that it gives you all of the different values, and you would be able to work each of these out. So you've got your enthalpy of solution, your entropy of surroundings, entropy of the system, and therefore your total entropy. And this is the one that's going to determine. And remember, we're looking for a positive value to get this spontaneous reaction. So sodium chloride and ammonium chloride, as well as magnesium sulfate and copper sulfate, all have positive entropy values when we're calculating the total entropy. So each of these is going to be soluble. On the other hand, silver chloride and calcium sulfate, these give you negative total entropy values, meaning that these are insoluble. So you can see that the magnitude of the total entropy of the system is for calcium sulfate is going to be higher than the entropy of the surroundings, meaning that's going to give us a negative value. And again, the magnitude for the surroundings, or the negative for silver chloride, is very high in comparison to the system, again giving us this negative number. So if we have a negative total entropy, the substance is insoluble. Now we can also look at how changing the number of moles in a reaction is going to affect the entropy. So if we increase the number of moles, we're actually then increasing our number of particles. If we increase the number of particles, this means that we're increasing the number of ways that the particles can be arranged. So our possible arrangements is increasing, meaning we have an increase in entropy, which makes our entropy of the system a positive value. And this can then lead to a total entropy value, which is also positive, meaning it would be a spontaneous reaction. But in this case, we're focusing on the entropy of the system. So if we look at the first reaction, you can see that we're going from 3 moles of reactants to 4 moles of products. So this is an increase in our number of particles, meaning the entropy of the system is positive. If I look at my second reaction, I'm going from 1.5 moles of reactants to 1 mole of products. So this is giving me a decrease in my number of moles, meaning my entropy of the system is negative. Now that doesn't necessarily mean that the entropy for the total wouldn't be positive. That would be something we would need to determine by looking at the entropy of surroundings as well. Now we can then use some of the information that we've learned to explain our solubility trends. Now you met the trends in solubility back in topic 8 when we're specifically talking about group 2, and you learned that the trend in the solubility of the group 2 hydroxides and the sulfates. Now what we can do is we can explain why this trend exists by using enthalpy values and entropy values. So remember, previously we said that solubility is going to depend on the entropy of the system. It's going to depend on the enthalpy of solution, and it's going to depend on the temperature. So when we look at the hydroxides, what we see is that the standard enthalpy change of solution becomes more negative as you go down the group. And this favours solubility because it makes my entropy of surroundings more positive. When you take the entropy of the hydrated ion, so when the ion has been surrounded by the water, now note we're talking about the metal, because the hydroxide is going to be the same in every single one of these, so that's not going to have an effect. We're looking at the entropy of the metal ion when it's hydrated. It also becomes more positive, which also favours solubility. So because both factors favour solubility, your metal hydroxides become more soluble as you go down the group. And we can prove that using enthalpy and entropy. So if we look at our values, as we said, we see this becoming more negative, which is a favour for solubility, and our standard entropy of the hydrated cation is becoming more positive, and that favours solubility as well. When we get to the sulfates, we have a slightly different story. So our standard enthalpy change of solution is becoming less negative. So this favours insolubility because it's making our entropy of surroundings more negative, meaning it's less likely to be spontaneous. The entropy of the hydrated ion still remains more positive as you go down the group. That hasn't changed, we're still using the same elements, therefore that favours solubility. So now we have 2 competing factors. So then we look at the magnitudes. So the overall decrease in the entropy of surroundings is 369 joules per Kelvin per mole. And the overall increase in the entropy of the hydrated ions is 148 joules per Kelvin per mole. So as the entropy of the hydrated ion is less than the surroundings, so the magnitude is much smaller, this is going to give us more negative total entropies, So that is going to become more negative as you go down the group. And the more negative it becomes, the less likely it's going to be soluble, meaning our group 2 sulfates are less soluble as you go down the group. So the magnitude of the surroundings is larger than the magnitude essentially of the system, favouring a non-spontaneous reaction. And we can see that when we look at the values. So you can see our entropy of solution becoming more positive, which favours insolubility instead of solubility, and this becomes more positive. In this case, that's favouring solubility, and the fact that the surroundings is going to be higher than our system would mean that this becomes less soluble. So let's finish off by looking at a past paper question. This is from the October 2019 paper. So we have ammonium nitrate being used as a fertiliser. And when it is heated gently at 160 degrees Celsius, the ammonium nitrate will decompose into nitrogen oxide and 2 moles of water. And we can see that we have an enthalpy value of minus 36 kilojoules per mole. So we know that that is exothermic. So we want to, first of all, predict the sign of the entropy change in system and then justify our answer. So we want to say, is the entropy of the system going to be positive or negative? So this is before we even look at a calculation. And the reason why is a couple of possible reasons. So we can look at the change in state, or we can look at our number of moles. So we can see that we go from a solid to 2 gases. This is going to give me an increase in my entropy, meaning the entropy of the system is positive because you have a solid reactant forming gaseous products. And that gives us our increase in entropy. We could also look at the fact that we go from having 1 mole of products to 1 mole of reactants to having 3 moles of products. So again, our entropy of system is positive because we see an increase in the number of moles. And that would give us more possible ways to arrange our particles, therefore an increase in our entropy. So this is a simple prediction without even thinking about a calculation. But of course, they will then move on to look at calculations. And we want to then calculate the actual entropy of the system for this decomposition, and we'll use data from the data book. Now this, please be aware, is from the old specification. So this uses the old data book. The 2018 specification has a new updated data book that does not include the entropy values, so you would be given these in the exam. But be aware, if you are doing old specification past papers, you need to use the old data book to make sure you have the correct values, and you can find that on the Edexcel website, or of course ask your teacher. So what we would do is we would look up the entropy values. So remember, we have entropy for each of our substances measured in joules per Kelvin per mole. So we would find that for the ammonium nitrate, the value is 151.1. For the N2O, it is 219.7. And for the H2O, it is 188.7. So our entropy of the system is equal to the entropy of the products subtract the total entropy of the reactants. Meaning I've got 219.7 plus, remember I have a coefficient of 2, so I have 2 times 188.7, and then I subtract my entropy of reactants, which is 151.1, and that gives you a value of positive, remember always include a sign, 466 joules per Kelvin per mole. And that would get you 3 marks. Remember, always show your working and show where you're getting all of your values from, why you're multiplying certain values. Make it all very clear so that if you do make an arithmetic mistake, you may only lose 1 mark as opposed to losing all of them. Then we want to calculate the entropy change of surroundings for the decomposition. So remember, our entropy change of surroundings is equal to minus delta H over T, and T has to be in Kelvin, remember. So our T is going to be 160 plus 273, because we have to change it from Celsius into Kelvin, and that gives us a value of 433. So we have our entropy of surroundings is minus 36 divided by 433. Now, the issue here is that this is in kilojoules per mole, so I can either convert it at the start or at the end. Now, I'm going to convert it at the start, so I'm going to actually turn this into 36,000 to make this joules per mole, divided by 433, and that gives me a value of positive 83.14 joules per Kelvin per mole. Okay, notice again, our 2 negatives are going to cancel each other out, and then that gives you your 3 possible marks. And then to finish off, we want to use the 2 values that we've just calculated to work out our total entropy. So our total entropy is equal to the entropy of the system plus the entropy of the surroundings. And we said that that was 446 plus 83.14, which gives us a value of 529.14. And it says we want to use a appropriate number of significant figures, and of course a sign and units. So this is a positive value. And if we want to make this into an appropriate number of significant figures, we would be given most likely 2 or 3 significant figures, because all of our values that we would have been using would be in 2 or 3. So let's change this to positive 529 joules per Kelvin per mole, and that's your 2 marks for your final answer. So there you can see the mark schemes for the first 2 questions, so giving us our values of our entropy of system, and then working out our entropy of surroundings and giving us our total final answer of plus 529 or plus 530, depending on your rounding in previous questions. Now that's everything for topic 12A, entropy. As I said, this can be quite a tricky topic to wrap your head around, because some of it is very much having to think in your head rather than being able to easily visualise it. I would strongly suggest that you practice past paper questions, because the majority of the questions are going to be your calculations. So make sure that you are confident in using these, and always check you're working closely on your calculator. Make sure to go back and check at the end of an exam as well. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon.